Welcome to This Explainer. Okay, today we are setting the stage for a deep dive into a truly revolutionary breakthrough in artificial intelligence. Seriously, if you've ever used an AI and felt like it suddenly, I don't know, lost the thread of the conversation or completely forgot a crucial document you uploaded just 10 minutes ago, yeah, you've hit a fundamental wall in modern computing. Today, we're exploring some brand new source material that outlines a brilliant way to shatter this exact bottleneck. It really brings us to the ultimate hook question. Why can't AI just remember everything? I mean, it seems like it should be simple, right? But underlying this question is a massive core tension in the world of machine learning. You see, developers are constantly forced to balance a model's ability to recall massive amounts of information with its need to actually run efficiently without burning through an insane amount of computing power. Historically, you really couldn't have both. But the top minds in the industry are actively tackling this massive bottleneck. We're unpacking a brand new research paper, spearheaded by scientists at Google Research. They've been relentlessly looking for a way to give AI a virtually flawless memory, all without breaking the computational bank. And, they definitely didn't do it alone. The Google team actually partnered up with experts from Cornell University and USC to publish this cutting-edge paper. Together, they're proposing a highly elegant solution that could fundamentally change how sequence modeling works across the entire industry. Section 1. The AI Memory Dilemma. The heavy brain versus the goldfish. Okay, let's dive into this. To understand the cure, we really first have to understand the disease. Right now, the AI industry is split between two main architectural philosophies for sequence modeling. And honestly, both have glaring flaws. It's a classic Goldilocks problem. On the left, we have transformers. Think of them as the heavy brains. They cache all past tokens, meaning their memory grows and they literally remember everything. But they have a quadratic computational cost. Mathematically, that's O of L squared. Basically, if you double the sequence length, you quadruple the computing cost. It's just way too heavy. Now on the right, we have recurrent neural networks, or RNNs. These are the goldfish. They use a fixed memory state, which makes them incredibly efficient with a linear cost of O of L. But because that memory is fixed, they're forced to forget past information as new data comes in. So one is way too heavy and the other is way too forgetful.
Section 2. Enter memory caching, the just right solution.
So we needed a hybrid approach, something that acts as the perfect middle ground. Let's define it. Memory caching, or MC, is a technique that enhances these lightweight recurrent models by caching checkpoints of their memory states. Instead of trying to cram an entire book into one single, fixed thought, it allows the effective memory capacity to actually grow alongside the sequence length. It elegantly interpolates, or finds the middle ground, between the fixed memory of those RNN goldfish and the infinitely growing but insanely expensive memory of transformers. Now, what's really interesting here is how visually intuitive this process actually is. Notice how the input sequence at the bottom is chunked into those colored segments. Instead of keeping every single token forever, or just throwing it all away, the model processes a segment, compresses it into a memory state, and then caches that specific state as a checkpoint. That's the gray box you see above. When the model needs to think, it doesn't just look at its current online memory in red, it can instantly reach back and retrieve info from all those beautifully organized compressed blocks of past cached memories.
Section 3. How to cache a memory. 4 aggregation strategies.
But hey, it's not just about storing the memories, right? It's about how the AI actually recalls them. Let's transition into the engine room here. The researchers didn't just propose the concept, they developed 4 distinct ways to actually aggregate and use these cached memory blocks during retrieval. And they build up in complexity. They start with residual memory, which is basically a simple summation, just adding the past memories directly to the current thought. Then we get gated residual memory, which introduces input-dependent gating to modulate exactly how much each past segment contributes. And from there, we move to the highly advanced context-aware mechanisms, memory soup and sparse selective caching. Let's look at memory soup for a second. I know memory soup sounds a bit like, an incredibly expensive tech bro lunch order, but it's actually a brilliant parameter averaging technique. Inspired by weight souping, this variant literally averages the parameters of the cached memory modules to construct a completely new, specialized, input-dependent memory. It's tailored exactly for whatever the AI is looking for in that specific microsecond. Pretty cool, right? Section 4. Sparse selective caching, the intelligent switchboard. Let's see how this builds into the most advanced variant they tested, sparse selective caching. If you're dealing with ultra-long sequences, say a massive 100-page document, attending to every single cached memory still gets pretty heavy. So look closely at the router right there in the center. Sparse selective caching uses this router like a hyper-intelligent switchboard operator. It dynamically measures the contextual similarity of the current token to all those past segments. Instead of lighting up the entire brain, it selectively connects only the top most contextually relevant past memories to the current thought. It's highly sparse, highly selective, and, honestly, incredibly efficient. The researchers also had to figure out how to slice the data. They tested both constant-size segments and logarithmic-size segments. What they found is that constant-size segments, those uniform blocks you see on the left, distribute the compression load significantly better. Logarithmic segments might seem computationally appealing at first, but they can force the model to compress excessively large early chunks, which eventually leads to memory overflow and degrading performance. Constant sizes just keep the resolution sharp.
Section 5. The needle in a haystack. Proving the tech. So, all of this sounds great in theory, but how do we anchor these abstract concepts in reality? Well, you test it. And the ultimate test for AI recall right now is the needle in a haystack task. Basically, you hide a random specific piece of information, like a passkey or UID, deep inside a massive, sprawling block of text, and you see if the AI can retrieve it. This is the huge wow moment of the paper. When they equipped the Titan's memory model with memory caching, it achieved a flawless 100% accuracy on the massive 16,000 context window passkey retrieval task. That's right, 100%. It didn't drop a single needle.
And this brilliantly illustrates exactly why this matters. Take a look at the baseline DLA model, a standard architecture in the second row. At 4K, it's doing great, but by 16K, it forgets drastically, dropping all the way down to 44% accuracy. It's just overflowing. But look right below it. Just by adding the sparse selective caching variant, that exact same DLA model jumps back up to nearly 77%. And the Titan's model with SSC, it stays locked at a perfect 100% across the board. Memory caching completely closes the recall gap with the heavy transformers. It's a game changer.
Section 6. Efficiency versus capacity. Faster and smarter.
But remember the Goldilocks problem? Having a great memory is really only half the battle. If it takes 3 days and massive server farms to run, it's just not viable. The model absolutely has to be computationally lightweight. Notice the steep gray line representing the standard transformer here. As the context length scales up toward 32K, its throughput, which is the amount of tokens it can process per second, absolutely plummets. It crashes. But the memory caching variants, represented by the blue and red lines, they maintain a beautifully stable high throughput. They are processing significantly more tokens per second than the heavy transformers as the scale goes up.
So the absolute crucial points here is this new mathematical complexity, O of NL. Because n, which is the number of segments, is just a fraction of L, the total length, the computational cost stays incredibly tame. What this really means is that we finally have an AI memory architecture that scales flexibly and powerfully, totally without breaking the compute budget.
Section 7. The future of AI memory, beyond the bottleneck.
Let's zoom out for a second to discuss why this breakthrough matters for the future. As AI models become deeply integrated into software development, legal analysis, and our daily personal tools, we are going to be feeding them millions of tokens of context. We simply cannot afford for them to forget the beginning of a document by the time they reach the end. This quote, directly from the researchers, reflects the core takeaway of this entire explainer. The era of being forced to choose between perfect recall and compute efficiency, it might finally be over. We can actually have the speed of the goldfish with the massive capacity of the heavy brain, dynamically scaling to whatever the task requires. It really leaves us with a truly exciting landscape ahead. If the memory bottleneck is completely shattered and an AI never forgets and never slows down, what incredibly complex, world-changing problems will we ask it to solve next? Think about it. Thanks for joining me on this explainer, and I'll catch you on the next deep dive.